In the last lecture, we introduced Shor's 9-qubit code, which attempts to correct both bit flip and phase flip or a combination thereof in a single qubit or A0 plus B1 that is being sent over a noisy channel. We had seen the coding circuit for such a situation, and we said that our purpose is to encode the state 0 as 0 logical, which is written in a compact form as plus plus plus, and 1 as 1 logical, which is written as minus minus minus, where the plus 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 stands for 0 0 0 plus 1 1 1 by square root of 2 3 times. So let us look at this circuit again. So this is the circuit which we talked about last time, where psi is the qubit which I am interested in sending, which has a structure A0 plus B1, and instead of sending the 3-qubit code, we have now generated a 9-qubit code in which we have done two parts. One is phase flip coding and the other one is a bit flip coding. And so at the end of it, what I got was a state which is A 0 0 0 plus 1 1 1 by square root of 2 written 3 times. That's how we have 9 qubits. So this is my coding actually. Plus B times 0 0 0 minus 1 1 1 by square root of 2. That's the, I am writing down a minus 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 bit. Okay. Now we need to correct for this. Like instead of doing a general theory, let me sort of tell you that we will assume this helps in analysis, but on the other hand, the discussion will be general so that any of the qubits you could take care of that. Now let us suppose that in the 9 qubits that you have received, I have a single qubit error, and that error is happening in, let us say, first qubit, which is both bit flip as well as phase flip. Now you have to realize that I am treating the 9 qubits as 3 blocks of 3 qubits each. And the special thing about the phase flip is the following, that even though I said that the phase flip has occurred in qubit number 1, but remember, I would not know the difference if the phase flip has occurred in qubit number 2 or 3 as well, because it will simply give you a relative minus sign between. So let's look at what happens. So we'll assume first qubit is flipped, both sides, sigma YL. Now in that case, what do I get? What I get as a result is this. Since the first qubit is flipped, instead of 0 0 0, I get 1 0 0 plus 0 1 1 by square root of 2, and into 0 0 0 plus 1 1 1. This now change occurs here. I will change the first qubit to take care of the fact that there is a phase flip also, but let me first write down what happens when I have got just a bit flip. So this 0 has become 1, 1 has become a 0, and the other two I will retain exactly the structure that they had. Now this is what would happen if I had just a sigma x error, but as I have said that I also have a sigma y error, so that would make this plus a minus and this minus a plus. This is the complete decoding circuit. So let me go on gradually analyzing this decoding circuit. So this is what we have received. This is what I wrote down. Because of the noisy channel, this what I showed there, that is what is received. Now it would help if we treat each of the three as one block. So let's look at what am I doing here. So here what I am doing is taking qubit number 1 as the control. I am applying a C0 gate on qubit number 2 and 3, and again taking qubit 4 as the control. I am applying a C0 on 5 and 6, and taking 7 as control. I am applying on 8 and 9. So what does it give me? So what I get is this, that A, now remember I have said that take the control to be the first qubit. So therefore I get 1, 1, 1 minus, now nothing happens here because the qubit number 1 had 0. So therefore they remain the way it was, this divided by square root of 2, this into 0, 0, 0 plus, remember qubit 4 is the control now, and that is already 1. So therefore these will become 0, 0 by square root of 2, and likewise this the same thing, 0, 0, 0 plus 1, 0, 0 by square root of 2. Not much is happening to the second and the third block because that's the way I am dealing with it. So this will now be 1, 1, 1 plus 0, 1, 1 by square root of 2, and these will be the same as before but with a minus sign. At that stage what we do is, go back to the slide again, that I apply a CC0 gate, taking the qubit number 2 and 3 as the control and applying a CC0 on qubit 1, likewise taking 5 and 6 as control on qubit 4 and 8 and 9 as control on qubit 7. So what I get now is, so this is the 3 CC0s that I apply. So I get A times. Now you remember how CC0 works. The CC0 will work if both the controls are 1, and this is exactly what has happened here. So therefore I will get 0, 1, 1 minus 1, 1, 1 by root 2. In this case, I will get 0, 0, 0 plus 1, 0, 0 by root 2, 0, 0, 0 plus 1, 0, 0 by root 2. And the second term is B times the same thing structure here, 0, 1, 1 but with a plus sign, 1, 1, 1 by root 2 and 0, 0, 0 minus 1, 0, 0 by root 2, 0, 0, 0 minus 1, 0, 0 by root 2. So this is, if you look at the slide, this is what comes out. Now what I do now is that I don't worry about what has happened to the second set of ancilla that I have put in, and concentrate only on the first qubit which was sent and the two sets of ancilla that I had introduced. So in this case, what will happen is this. I could carry on writing all the 9 qubits, but it's actually not particularly important. So I will now, because we are, whatever was their status, they remain as it is. So what I will now do is to simply look at what this state was. Look at this state. You can actually factorize, you notice this. This state is equal to A times 0 minus 1 by square root of 2 times 1, 1. This is qubit 1, this is the pair qubit 2 and 3. And 0 plus 1 by square root of 2, 0, 0. 0 plus 1 by square root of 2, 0. And likewise, B times 0 plus 1 by square root of 2, 1, 1, 0 minus 1 by square root of 2, 0, 0, and 0 minus 1 by square root of 2, 0, 0. As I said, I ignored the second set of qubits that I had introduced, and I will be now looking at only the first, the fourth, and the seventh qubit. If you look at the slide again, you notice that on each one of these, I have introduced a Hadamard. Look at what the Hadamard is going to do. A Hadamard applied on qubit number 1 is going to make it a 0, because this is 0 minus 1 by root 2. And on this one, on this term, it's going to make it 1. And these things I will ignore. They will remain what it is, because nothing has been done to this. So therefore, after the set of 3 Hadamards, I get the following. I get A times, remember this was 0 minus 1 by root 2. So therefore, let me write it as 1 on a Hadamard. And just to make sure that I am talking about line 1, I have indicated that. Then the fourth one is 0. And the seventh one is also 0. Plus B times 0, 1, and 1 on the fourth and the seventh. This is what happens if you look at the slide which has 3 Hadamard. Now what am I going to do at this stage? I am going to take, remember that my interest is actually in qubit number 1. So I am going to take qubit number 1 as the control and apply a C0 on the qubit number 4 and qubit number 5. So let's do that. So C0. Now that gives you a 1. Since the control is 1, this 0 becomes a 1 and this 0 also becomes a 1. Plus B times, this is a 0 and this also remains 1, 1. So this is qubit 1 and this is qubit 7, 4 and this is qubit 7. The last bit of an action that I need to do now is obvious, because you notice that what I have got here is 4 and 7 having 1, 1. That's actually telling you that I could use this pair to apply a CC0 on the qubit 1 which I was interested in to begin with. So therefore, we apply CC0 and that will make it A 0, 1 plus B 1 And this, if you recall, is the original qubit that was sent before I did coding and then decoding. And this is roughly what the whole structure is about. But let us conclude this with a general policy, because I have illustrated it for only qubit number 1, but as you could see that what I am hinting is that you could do it for anything. So let's see what does one do. So if you remember that what I had was a 0 encoded as 000 plus 111. Instead of writing 3 times, let me just put our usual notation of 3, and the 1 was encoded as 000 minus 111. Supposing a bit flip has occurred. How do you take care of a bit flip? How do we check first? On which bit the error has occurred? Remember, I worked it out for qubit number 1. But on the other hand, how did I know to begin with that the error actually has happened there? And the way to do it is this, that I want to check parity. I want to check parity in the following way. I compare one and 2. Now, when I compare the parity of 1 and 2, I get either a +1 or I get a -1. Now, since I have already made a statement that at best I have 1 error, only when I get a -1, then I know that the error has occurred in one of the qubits, and that could be either one of them. Then what I do is compare 2 and 3. Now, this is very trivially done, comparing 1 and 2 by finding out what is sigma z1, sigma z2. And similarly, if I want to measure 2 and 3, I just do sigma z2, sigma z3 measurement. Now, here again, I can get a +1 or I can get a -1. Now, notice what are my possibilities. So, the possibilities are, I get a +1 here and a +1 there, which means no error has occurred. I get a +1 there but a -1 here. Now remember, +1 here meant 1 and 2 did not have any error. But if I got a -1 here, it means that I have an error in bit 3. Now if I have a -1 there, then either bit 1 or bit 2 have an error. But then if I have a +1 there, bit 2 doesn't have an error, and hence 1 must have had an error. But if I get a -1 there, then it means either 2 or 3 must have an error. And since from the first argument we have given either 1 or 2 has an error, so therefore 2 has an error. And likewise, I can find out if the error occurred in bit 3 or not. And suppose I am talking about now a phase flip error, then what I do is to compare 1 and 2. And this I do by sigma x1, sigma x2, sigma x3, right up to sigma x6. And also do 2 and 3, which can be done by doing sigma x4, sigma x5 up to sigma x9. Now I am not going to work out as I did for the previous case, but I leave it to you to work out that this will enable you to find out where the phase flip has occurred, and if a phase flip has occurred, it can be corrected by applying a sigma z naught. I should have said in the first group, when after I found out which qubit has had an error, I could have corrected it by applying sigma x. And here by sigma z. Okay. Now suppose this analysis leads me to conclude that there has been both a phase flip and a bit flip, then each one of the corrections must be sequentially applied, because as you can see they are not interfering with each other. So this is essentially a brief summary of quantum error correction code, which has very important consequence in communication, because keeping the purity of a quantum state is of utmost importance in dealing with any quantum algorithm.